Lesson 92. Independent and dependent events. Conditional probability. In the study of probability, we can classify events as whether they are independent or dependent. Independent events are the ones that when one thing happens, it will not affect the outcome of the next or other events. For dependent events, it's obviously when one event happens, it will have an impact on the occurrence of another one. We're going to illustrate the difference by looking at two examples below. Let's start with tossing two coins. So when you toss two coins, will the outcome of the first coin affect the outcome of the second coin? No, right? I hope you said that. So let's write this down. These are independent events. Okay, so let's draw a tree diagram to represent these. What can I get when I toss the first coin? Heads and tails. What will I get when I toss a second coin? Heads or tails. But whether I got head in the first coin toss or a tail in the first coin toss, I will still get heads and tails. What we can also include on the tree diagram is the probability of heads and tails occurring. Assuming that this is a fair coin, then I must have a half and half chance of getting heads or tail. And so is here. Okay, so let's list out the outcomes. So I get either heads, tails, tail, head, or tail, tail. What is the probability of getting heads and heads? It is 1/4 because all these outcomes are equally likely. Right? And then getting heads, tails, tails, head, or tail, tail, I also get 1/4, 1/4, 1/4 as the probability. If I look a little closer to the individual probabilities of getting a head from coin 1 and getting a head in coin 2, how can I relate 1/2 and 1/2 to 1/4? It turns out I can multiply these weights on the branches of the tree diagram to come up with having a head and a head. So two events occurring together. What we have illustrated here then is that for A and B that are independent events, we can say that the probability of A and B is equal to the probability of A multiplied by the probability of B. So this is a multiplication. Okay. Example 2. An urn contains 3 red marbles and 5 blue marbles. 2 marbles are drawn one at a time without replacement between draws. Are these dependent or independent events? Well, let's think about this, right? We can even start by doing part B, which is to draw a tree diagram. So the two colors that I have are red and blue. Okay. There are 3 red marbles and there are 5 blue marbles to begin with. If the first marble is red, when I reach into the urn again without having that red marble replaced, then I will still get red or blue. However, how many red marbles are left in the urn now? Only 2 because one of them is gone. And to start with, I had 8 marbles in total, but now I only have 7 marbles. Does that make sense? But I know there are still 5 out of 7 marbles that are blue. If the first marble drawn was blue, I may still get a red or blue marble in the second draw, but now I have 4 blue marbles out of 7 versus 3 red out of 7. Okay, so the outcomes here are red, 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 blue, blue, red, and blue, blue. Okay, because of this, we know it's quite clear that these are dependent events. Okay, let's calculate the probability of getting each event. Getting a red first, 3 out of 8, and so we multiply. Getting a second red is now 2 over 7, so 6 out of 56. Red, blue, 3 over 8 times 5 out of 7, 15 over 56. Blue, red is 5 over 8 times 3 over 7, 15 over 56 again. 5 out of 8 times 4 out of 7, so 20 out of 56. Okay? What we should note is that since there is a difference between, when we talk about independent events, the first coin toss in the last example, we can call it, probability of head, and then the second probability of head again, or H2, like the second head. But now here we have a special notation to describe the second marble drawn. Since the draw of the second marble depends on the very first marble, we use this notation to indicate that the probability of getting red second time, the subscript is what we add because we don't want to mix up the first red and the second red. But here the key is given. So knowing that the first marble is also red. Okay, so we can say that this 2 over 7 probability is the probability of getting a second red given that we know the first one is also red. Okay, the 5 over 7 here, then we can call this probability of B2 given R1. Okay, and so on and so forth. This means that I can calculate the end of 2 dependent events A and B using P of A and B equals to P of A times P of B given A, because A is the condition. If I rearrange this expression, I will get a formula for calculating what we call the conditional probability. P given A equals to P of A and B divided by P of A. But then we also know that if A and B are independent events, we can also claim that the probability of B given A is just the same as the probability of B, right? It has no effect based on what happened first. Okay? Example 3. Draw 2 cards from a deck of 52. Find probability of getting 2 aces if the card is replaced between the 2 draws. So first we need to decide whether the second draw is affected by the first one. Well, if I'm replacing my first card, do I notice a change in the deck before I pick my second card? Not really, right? So these are independent events. So let's calculate the probability. First card, 4 aces out of 52 times 4 aces out of 52. These are both 1 out of 13 times 1 out of 13. So you get 1 out of 169. Part B. This time, we're not replacing the cards between draws. Well, it's pretty obvious now that after I pick the first card, I'm going to have 1 fewer card in the deck. That means the second draw will be affected. So these are dependent events. And as such, the probability will be 3 out of 51 for the second card. And this works out to 1 out of 221. Now, in part C, what if I draw the cards together simultaneously? Well, think about the two cards now you're holding. Okay, card A, card B, but order doesn't matter. If card A is an ace, does it affect the fact that card B was picked from a slightly different deck without card A? Right? So once again, this is also an example of dependent events, which will have the exact same probability as part B. Let's take a look at number 4. Toss 2 6-faced dice. Find probability that the sum of 8 is find the probability of the sum of 8 given the sum is even. So here is a dice table. Where are the sums of 8? They are down here. Okay. So if I claim that this is event A, then sum of even is event B. How many even sums are there? I think you can tell that half of the sums are even, so 18 out of 36, right? So we know that here we're looking for A given B, and based on formula, we have P of A and B divided by P of B. So the condition always goes at the bottom. Sometimes this is known as the reduced sample space. You're only looking amongst the even numbers, okay? So P of A and B, that means it has to be 8 and even. So all the 8s are even, so 5 out of 36. And then probability of getting even sum, that's 18 out of 36. Simplifying this, we get 5 out of 18. Okay. Part B. Find the probability of the sum is even if the sum rolled was an 8. So this time, we're going to use the same letters A and B to represent the same events. But we're really dealing with P of B given A. So we're switching the condition, right? We're looking for an even sum, knowing that we rolled an 8. So theoretically speaking, we have P of B and A over P of A. So this time, well, even and 8 is still 5 out of 36. But what is P of A, the probability of rolling 8? It is 5 out of 36, which is 1. So it is important to note from this example that P of A given B is not necessarily equal to P of B given A. Okay, so please note that. Here is number 5. Ms. Kuhn plans to go on a 3-day camping trip at Kildare Provincial Park in Ontario. She either goes hiking or visit a beach each day, but she wants to pick a different location each time. There are 3 hiking trails and 8 beaches at the park. Draw a tree diagram to represent Ms. Kuhn's itinerary. Okay, so it's not too bad. Hiking or go to the beach. All right, what have we got here? We have how many choices? 8 plus 3, 11 choices. On the first day, she can either go to any one of the 3 trails or any one of the 8 beaches, but 11 locations altogether. We're going to a different location each day, meaning that if I've gone to the first hiking trail, I will only be left with 2 choices on the next day out of the 10 remaining locations. So we can fill out this tree diagram as such. So there are still 8 B's. And then I have 3 trails that I can still go to here, but only 7 beaches that I can choose from. Okay. And then I can do the HBs like that. Okay, so we're still reducing the number of total locations that we can visit and total number of hiking trails. Now it's down to 1, but still 8 B's. Here I have 9, so 3, so 2 out of 9 hiking trails, low locations, and 7 out of 9 here. And then the next one, BH, so 2 out of 9, 7 out of 9. And then lastly, 8, 7, so 6 out of 9 versus 3 out of 9. Okay. So let's find the probability of not going on a hike on all 3 days. We can see that we have one itinerary where we go hiking on all 3 days. So I think it's more efficient if I do the 1 minus P of HHH. This is really an and. Remember that. So 1 minus 3 over 11 times 2 over 10 times 1 over 9. Okay? And then what does this work out to? 164 out of 165. Number 2. Probability that she spends exactly 2 days on the beach and 1 day hiking. So we need to pick out all of these routes here. So 2 B's, 1 H. I have this one here, and then I have this one here, and also this one here. Okay, so 3 different paths that needs to be considered. So this is P of HBB plus P of BHB plus P of BBH. Okay. For each one of these routes, we have 3 out of 11 times 8 out of 10 times 7 out of 9. That's the first case. Second case, beach first, 8 out of 11, 3 out of 10, and 7 out of 9. Last case, 8 out of 11, 7 out of 10, and 3 out of 9. Using my calculator, I got 28 out of 55. Number 3, probability of spending at least 2 days on the beach. So that means either 2 or all 3 days. Okay. So from part 2, we already found out that 2 days on the beach is 28 out of 55. So we'll use that number. Now we just have to add the second case, which is spending all 3 days on the beach. So 2855 plus, that would be 8 out of 11 times 7 out of 10 times 6 out of 9 works out to 28 over 33. Part 4. Find a probability that Ms. Kuhn spends at least 1 day on the beach if she went hiking on the first day. So here we notice that in this question, we're looking for a conditional probability, right? Because we're restricting ourselves to the fact that we only care about cases that begins with hiking on the first day. What we learned in this lesson is that, well, when we calculate conditional probability, we can do at least 1 day on the beach, so greater than or equal to 1. These are just shorthand, they're not formal notations, given that our first day was spent hiking. We could then use the formula that we have learned. The end of the two events, probability over the probability of the condition H1 in this case. How many of these outcomes involve spending more than 1 day on the beach and also starting with hiking? So let's go back to the tree diagram. We are thinking about the stuff in the purple box. Out of those events, which cases are included? It would be HHB, HBH, and HBB. We have P of HHB, P of HBH, and P of HBB. Okay. And out of P of H1. And this is 44 out of 45 if I use my calculator to do that. Another way to look at this question is to consider, that purple box kind of shows me that the bottom half of the tree diagram is not relevant. Really, I'm just choosing from, the 3 hiking trails and starting from that top half. And out of that top half, I now have a smaller tree diagram. The smaller tree diagram looks like this. Right? And instead of looking 3 cases, adding them together, I can subtract the complement, which is HH, which simplifies my calculation by a lot, because this outcome, P of H2, H3, is 2 out of 10 times 1 over 9. And this is also 44 out of 45. Let's consider the last example, example 6. In a school, all students study math and English. If 88% pass math, 93% pass English, 4% fail both, represent these events using a Venn diagram and a contingency table. So if I use a Venn diagram, I know one region for sure, which is students who failed both subjects. They won't belong to the 2 circles. That means 4% goes here, okay? But all I know is 88% pass math and 93% pass English. But there's no way for me to know, at least from the question directly, how many students failed or passed both subjects, okay? So let's label X, Y, Z. And all I know is X plus Y are the ones who pass math, which is 88%. And Y plus Z is 93%. Okay? That's all I know. Let's take a look at another tool, a graphic organizer called a contingency table. The way it works is this. You're going to list your events, M, math, passing math, failing math, so M prime. Passing English, failed English. And then the last column and rows are totals. I know that the total population is 1. I know that in total 88% of the students pass math, so this must be 0.88 as a total for the math column. Same thing with English, this must be 0.93. But the advantage of using this visual is that column or total row should add up to 1. I have 1 minus 93, or 0.93, which is 0.07. Here, 0.12. Right? Now, what else can I find? I know that 4% failed both subjects. So, math failed, math prime, E prime. This must be 0.04. Now I think I can work out more numbers, right? Because in the math prime column, we have 0.12 minus 0.04, which is 0.08. And then in the English passing column, I have 0.93 take away 0.08 to give me the E and M section, which is 0.85. And then the last entry must be 0.03. Part B, find the probability of passing both subjects. So from the contingency table, I can easily tell that we're looking at the 0.85 section. So let me write this down. But if we use the Venn diagram method, then we are looking at the probability of M and E, which involves finding 0.88 plus 0.93, the individual events, minus the OR of all the events, which is 1 minus 0.04. So we're utilizing that formula, and this will also give me 0.85. Okay. Part C. Find the probability of passing math given that the student passed English. So it looks like this is fine probability passing math given they also passed English. We can use the conditional probability formula as such. So remember the condition goes at the bottom. And this is 0.85 over 0.93. In other words, 85 over 93 if we write it out properly. Part C, justify whether passing math and English are independent events. There are two ways to do this, okay? So you can either compare from the very first page of this lesson, is the conditional probability equal to the probability of passing math, the subject here, okay? So what's the conditional probability? Now 85 over 93 should give us 0.91397. That's from my calculator. And then probability of passing math was given to us as 88. So the conclusion here is that since M given E is not equal to P of M, then therefore the events are not independent. Okay. Another method to do this, which is my personal choice, I don't know why, but it's a habit, I guess, to compare P of M and E to, this is really assuming that M and E, or passing math and passing English, are independent events, because the end of two independent events can be calculated by multiplying the individual probabilities, right? So here, the end of the two events is 0.85, and then passing math is 88% probability, and passing English is 93% probability. This works out to 0.8184 ... and obviously is not equal to that. Okay, so since P of M and E does not equal P of M times P of E, and then you have the same conclusion that they are not independent. Okay. So the bottom here, we have a list of axioms for probabilities. We have been talking about these and applying these in our problem solving in the last two lessons. Just make sure that you're familiar with them, and I will not ask you to memorize or recite them whatsoever on exams, but just understand that, as part of the knowledge framework for math, Math is built on axioms, and all the work that we have been doing are based on all of these universally true rules. Okay?